Hello. Tonight we're going to talk about water potential. What is water potential? Water potential is the movement of water from a high concentration to a low concentration and the force that moves it. It can be used to do lots of things, like this is a plant that has a very low water potential, so it's all wilted. But if you were to put it in a container of water, put the water up to about here or so, the water would move back into the plant, making it look like this. It's called, this is called turgor pressure. That's the pressure of the water against the cell wall. Water potential is the combined effects of the solute concentration and the physical pressure against the cell wall. It's measured in psi, which is this trident symbol, and the unit that we're going to be measuring it in is megapascals. 1 pascal, now this is a lowercase p, is 10 atmospheres of pressure, and this is a megapascal, so it's quite a bit more. There's a formula for calculating water potential. Water potential, which is the psi symbol, is equal to the pressure potential of the pressure against the cell wall plus the solute potential. Now, many times we're going to have a pressure potential of 0 because we're going to do it in an open container, not inside a cell wall. So pressure potential might be 0, in which case the water potential will equal the solute potential. Solute potential is also called the osmotic potential because it's the direction that the water is going to flow, the force behind it. Because if you have a high concentration of solute on one side and low on the other side, that means on the other side there's a whole bunch of water. So the water is going to go back to dilute the concentration of solutes. The solute potential of any solution is measured in atmospheric pressure, and it's always negative. Why? Why do you think it might be negative? Oh, probably because the answer's on your paper here. Because there's less free water molecules to do the work on the other side, on that side. If there's more water that's attached to the higher concentration of solutes, then there's less water that can move freely, and so it's going to be negative. So here's what happens to the water molecules. If you have a whole bunch of solutes, so here's a solute, ammonia, that ammonia is going to be attracted to the water molecules, and the water molecules then are bound to the ammonia to dilute it, to bind to it, and that means those molecules aren't able to move across the membrane to dilute solutes. Pressure potential is the physical pressure on the solution. Again, this can be positive or negative, but many times it will be 0 if we have an open system. A negative one would be something like transpiration going on in the tissue of the plant where it's creating a suction. And so the water is being transpired out of the top of the plant, and so the suction is pulling it up. That's kind of a water tension thing. It can also be positive in a living plant where there's a lot of turgor pressure, where there's a lot of water in the cells pushing against the cell wall. Psi, water potential, is measured against pure distilled water. Not tap water, because there are minerals and solutes in tap water, but pure distilled water. That's the standard. That's 0. Pure water is, like I said, is 0. Anything else is going to have solutes in it. Psi is measured at an atmospheric pressure of 1, and then it's 0. Okay, we're going to look at an artificial model because it's really hard to look at a cell. Okay, you can't stick a little probe inside a cell and measure it very easily. So we'll look at an artificial model. Here's a glass tube with a membrane in the middle, pure water on one side, and a solute concentration over here, 0.1 molar solution of any solute. Could be salt, sugar, whatever. Okay? So, to figure out, because this is an open container, it's not sealed, the pressure potential is 0. The solute potential is a negative 0.23. and I will show you how to calculate that in a minute. Okay, so then what then is the water potential? Okay, the water potential on this side is a negative 0.23. Because this is pure water, the water potential on this side is 0. What direction is the water going to go? It always moves from high to low. Well, 0 is a higher number than a negative 0.23. So the water is going to go from high to low, and it's going to move this way, and so the water does. Okay, now that's moving from a hypotonic solution, to a hypertonic solution. Hypo has less solute, hyper has more solute. Okay? So, if we add a plunger that seals off this side, and I push on it, so now I'm putting in a pressure potential. Okay? If I put pressure potential of 0.23, then this side is 0. There is no net movement of water. No net movement of water. That means some water is going to go this way, some water is going to go that way, and it's going to be a net gain of 0. If you continue to plunge on this side, so no water comes back up, the solutes are going to become more concentrated. That's true, but if you push hard enough, you will have more water being forced through the membrane out to this side. And so in this case, a pressure potential of 0.3, solute potential of a negative 0.23, gives you a water potential of 0.07, which is bigger than 0, and so now the water is going to go the opposite direction. Okay? Now, you can do it the other way. You can create a suction, and that's what this one's showing. If you create a pressure potential of a negative 0.3, so you're sucking it up, you can pull the water from the other side over. Again, pressure potential of 0.3, solute potential of 0, water potential of a negative 0.3, smaller than a negative 0.23, so the water is going to move that direction. Now let's look at it in a real life plant, what really happens with plants, okay? Or any cell for that matter. Okay, so here I have distilled water. My pressure potential is 0 because it's an open container. My solute potential is 0 because it's distilled water. So my water potential is 0 because 0 plus 0 is 0. Okay, so we know that. Now, on the plant itself is a flaccid plant, which means a lot of the water has already been sucked out of the plant. It's drying or something like that, and so it's flaccid. It's limpy. Okay, pressure potential is 0. The solute potential, it's been calculated for you, is a negative 0.7. Well, 0 and negative 0.7 is a negative 0.7. You put that cell inside here, and then the cell will reach equilibrium when the water is going to move from 0 to negative 7, so from high to low, water is going to move into the plant, and when it does, it pushes against the plant cell wall. When that pressure on the plant cell wall is equal to the solute potential, so negative 0.7 solute potential equals a positive 0.7 pressure potential. When those two numbers equal, the equilibrium is reached because the water potential then of the plant is 0. So the pressure of the water on the cell wall is equal to the solute concentration inside. It will be 0. And at that point, the plant becomes turgid, which means firm, filled with water, and very firm. Now, at that point, equilibrium is reached, and water goes in and water goes out at an equal rate. It does not mean water stops moving. That's a big misconception that students have, so please don't think that. Equilibrium, both move in both directions. Let's look at another situation. Okay, we have the same flaccid cell to begin with. Okay. This time, however, I don't have distilled water. I have a 0.4 molar sucrose solution. So my solute concentration is a negative 0.9. Now again, I will teach you how to calculate that. Okay, so it's my water potential out here is a negative 0.9 megapascals. Out here, it's inside the plant, it's a negative 0.7. So negative 0.7 is bigger than negative 0.9. So water is going to move from the plant into the sucrose solution to try and dilute it. Okay? When the water does, the water is going to leave, and that causes the cell membrane to pull away from the cell wall. That's called plasmolysis. So it's pulling away, shriveling up on the inside of the plant. That's what happens when a flaccid cell is placed in a hypertonic solution. The water potential forces the water to go out of the cell, resulting in plasmolysis. Okay, to be able to calculate solute concentration, this is what you will need to be able to do on the test and on the national exam. Okay, so here's what happens. You have your solute concentration is equal to, and here's a formula from chemistry, a negative I CRT. I is the number of molecules in the solutes. Okay, so for example, how many molecules the solute breaks down to when it ionizes in water is really what it is. It's the ionization number. If I look at sucrose, sucrose turns into sucrose. It doesn't ionize into hydrogen and oxygen and carbon. Okay, it stays as sucrose, so its ionization number is 1. Sodium chloride, which is another one that those two are the ones they often test you on. Sodium chloride breaks down into sodium molecules and chlorine molecules. And so that has an ionization constant of 2 because you form 2 different molecules. Okay, so that's your ionization constant. C is the molar concentration. How concentration are the solutes in that solution? R is a pressure constant that does not change. It's 0.0831. Okay, 0.0831. That's a number you're going to have to remember. Temperatures, the temperature is T, but it's in Kelvin. So what you do is you take 273 plus your temperature in Celsius. So if the temperature in Celsius is 27, then your temperature is 300 in Kelvin. If it's 25, then it's 298. So you just need to be kind of aware of what the temperature is. Make sure you put it in Kelvin. Okay, now, literally, our values for pressure potential are almost always going to be 0. So let's consider this 0. So your water potential is going to equal your solute potential. Okay? Now, some things to remember. Water always moves from a high water potential to a low water potential. It moves from a hypotonic solution to a hypertonic solution. Solute, the term solute is related to the osmotic pressure, and pressure is related to the pressure potential. Pressure raises water potential, and when working problems, use 0 for pressure potential in animal cells and in open beakers. Now, plant cells, they may not be. So it just depends. And 1 bar of pressure is equal to 1 atmosphere. Okay, in class, we will be doing several problems. I want to be there when you do these to help you. We're going to be doing several problems where you're going to be using this formula, using this information to be able to solve water potential problems. We have a whole lab that deals with this. Okay, so have a wonderful night. See ya.